So Newton cooling law. Newton observed that the cooling rate of an object is proportional to delta T, which is the temperature difference relative to the ambience difference, the temperature of the environment. So let's write here the cooling rate of an object is proportional to delta T, which is the temperature difference say the temperature of the object I was trying to find a shorter way to, a more compact way to write it, and the ambient. All right, so so let's define the following component that will come to will take a role here. We play a role in deriving this law. T of T, we have a multitude of T's here. T of T will be the temperature of the cooling object. Okay, T sub 0 will be the initial temperature. Okay, T sub S will be the environment or the ambient temperature. By that we mean, when I talk about the example, the cooling inside the refrigerator, then T sub S will be the temperature setup of the refrigerator. In the example that I gave you on the board, it's the 35 degrees Fahrenheit. Okay? Now, what Newton says, or Newton's claim, said that the rate T prime is proportional to delta T. This can be written as the following. If you remember the RDR and RGR, if you use the same terminology, then there is a constant K, because of the constant of proportionality, that will be equals to T prime, but not divided by T as we had before with RGR and RDR, but T prime divided by delta T. And this is the ratio that we were talking about. Go ahead, Michael.
What it says, derivative of T prime.
This is,
alpha sign?
that's proportional, symbol for proportionality. We saw it last time. We can write it as T prime is proportional, is K times delta T. That's what we did at the beginning when introducing exponential growth and decay. Okay? So, now compare this to...
So delta T is change in temperature?
Delta T is the temperature difference.
Okay. So it's T of one minus T of the other.
Right, right. I didn't define delta T, so you're right. I should have said so. So let's write where delta T will be the difference between T of T minus T sub S. The difference between the difference between the temperature of the object and the ambient temperature. Actually, it's going to come soon because we're going to define a function that we're going to substitute delta t. Now, let's compare this. So let's call this equation 1. Okay, so compare 1 to what we had before when we had k was equal to y prime over y, right? So we are looking at k equal t prime over delta t, and now before we had y prime over y. So we want these to look like that, and in order to accomplish this, we're going to define a new function. We're going to define a function y of t, and we're going to say that y of t will be the difference. Y of t will be t of t minus t sub s, or delta t. Okay, so now we have what we had before. Well, before we go further, because y of t equals the difference, and remember t sub s is a constant, so when we take y prime, then y prime will be t prime minus the derivative of t sub 0, but since it's a constant, it's simply going to be t prime minus 0 is simply t prime. Okay? So now we can have k, instead of t prime over delta t, t prime is the same as y prime, and delta t is y. And we are back to what we had before when we dealt with exponential growth and decay. So essentially what the Newton Cooling law, or the heart of the Newton Cooling law, is this substitution, is the creation of new function, which is the difference between the temperature of the cooling object and the ambient temperature. So the idea behind this is when you deal with this, with the phenomena that involve cooling, and actually heating as well, instead of dealing with the temperature, you define the function y, and then you treat it as a standard exponential growth or decay. You solve for y, and you don't forget that at the end of the day, you need to go back to t by reusing the definition. Okay? I think I have a very short example for you. I think it's short. And I'll try to squeeze it here. I'll do at least one part. Okay? So here's the example. By the way, what is the solution? Because we have k like that, then we're going to say that the solution here, y, is our standard y sub 0 e to the kt. We solve for that, and now we need to we can reverse the process, and once we solve for y, we can go back and solve for t. So here's a quick example. It's a multiple part example, but I'm going to do just the first part, and I'll continue next week. Given T sub 0 equal 72 degrees, the initial temperature, and this is a room temperature here. So we're probably going to take something similar to what I said before. T sub s is 44 degrees Fahrenheit, and this will be the refrigerator temperature. So my refrigerator was set way too low when I said 35. 44 is more like it. And let's say another data that we have, that after 30 minutes, if we measure the temperature of the object that we put in the refrigerator, then its temperature was 61 degrees Fahrenheit. So this is the temperature after 30 minutes. Okay, and what we want to find, let's find, I'll do the first part, find T after 60 minutes. Okay, so let's see how we work out the solution here. Again, the picture is the same as I put on the board, where this is T of t in Fahrenheit, and this is the time, let's say in minutes. So we start with 72 degrees, and we know that we'll go down low to 44 degrees, and this will be the final temperature of the object. So we start with room temperature here, and the temperature we're going to drop like so, and we know that after 30 minutes it will be 61 degrees. So let's put 61 right here. So this is after 30 minutes. Okay? And we want to know what happened after 60 minutes. You probably want this page back, would you? So let's set it up. Let's say we know that y equals t minus t sub s, or in our case t minus 44. Right? T sub s is 44. We are given that. And what is y sub 0? Well, y sub 0 will be t minus t sub 0, right? I'm sorry, it will be t sub 0 minus t sub s by definition. So it will be 72 minus 44, or 28. So we have y sub 0, and what we know that after 30 minutes, y after 30 minutes will be t after 30 minutes minus t sub s, and t after 30 minutes was 61 degrees, t sub s is always 44, and the difference is 17. Okay? So now we make the connection, we say because the model is y equals y sub 0 e to the power of kt, then we let t equal 30 minutes, and we solve. So after 30 minutes, y of 30 minutes is 17. So we have 17 equal y sub 0, which is 28, e to the power of k times 30. Divide by 28 and apply the natural log, as we've done before, and you have the natural log of 17 over 28 equals 30k, natural log of E, of course. And K, the cooling rate, K is 1 over 30 times the natural log of 17 over 28. Again, you may calculate the number here, but you risk, because 17 over 28, or the natural log of 17 over 28 is a rational number, you introduce rounding error. I prefer not to do so. Just in case you're wondering, this is approximately negative 0.01663 if you want to round it to 5 decimal places. But notice that it's rounded. So now we have the model y of t equals 28 e to the power of this one, 1 over 30 natural log of 17 over 28 t, right? And we want to solve after 60 minutes, t equals 60 minutes. And we're going to say that y after 60 equals 28 e to the 60 over 30, I don't know if you see it, but it will be simply 2. Let's write it like twice. 1 over 30 natural log of 17 over 28 times 60, which is the same as 28 e to the power of 2 natural log 17 over 28, right? And this is a number that we can calculate. And at this point, I'll calculate it, and it will be 10.3 degrees Fahrenheit. But what is the temperature of the object? Y of 60, by definition, is T after 60 minutes minus T sub S, right? So T after 60 minutes will be Y of 60 plus T sub S, or 10.3 plus 44. So the solution is 54.3 degrees Fahrenheit, which makes sense. We know that the temperature cannot be lower than 44 degrees, right? But it has to be less than 61 degrees because it took 30 minutes. So here's another thing, if you just a parting comment here. Remember I told you about the difference in rate, that at the beginning the cooling is fast and then it slows down. Look how fast. We started at 72 degrees. The first 30 minutes we went down from 72 to 54. 18 degrees difference. I'm sorry, we went from 72 to 61. 11 degrees difference. The next 30 minutes we went from 61 to 54, only 7 degrees, on the same period of time. So, yes, the cooling rate has slowed down. Guys, thank you. I'll see you on Friday.